as you see. First, I will define my starting point, then how there has been a move from industrial to assistive robotics, and this poses several research challenges, which I will explain. Then I will focus on the CLOTHILDE project, on how computational topology and motion learning can be combined in order to manipulate clothing in a nice way, say, versatile way. And at the end of the presentation, I will explain some of the social and ethical implications in robotics and AI. At the end of the third point about the CLOTHILDE project, I will ask for questions if you like to ask. And also at the end, after the ethics presentation. Starting from our starting point, as you know, we are at the Institute de Robòtica Informàtica Industrial, which is a joint venture of the Council of Scientific Research of Spain and UPC, the Polytechnical University of Catalonia. We are about 100 people working here, and one of our important task forces are robots. Today you will hear a lot about all these kind of robots, and tomorrow also. And you'll see that we at the Perception and Manipulation Lab, what I will present today, we work with this type of robots. But we have many others, like leg robots, wheeled robots for outdoors, humanoids for education, etc. So this is our research group, the group that works mainly on assistive robotics. And I always like to show how many women we are, because you know that in technology in general, there is a shortage of female researchers. So I encourage those of you that are here attending the course to really get involved. And you will see at the end that we are hiring also. So if you know people, not just women, that like to work on these technologies, let us know. This is our lab. You see that we have built this assisted living facility inside the lab that is made of two rooms. One is a bedroom. You see that we have a bed, a small table, and a cupboard with a mirror that makes vision, that yesterday you were talking about vision, quite difficult. And also we have another room that is a living room, kitchen, dining room all together, and two robots that do services in this environment. For instance, what type of services they do? One is setting up the table, for instance. And you will see later that one of our specialties is to manipulate clothing items. Why? Because in these assistive environments, this type of deformable objects are very present. And this entails a big difference with regard to manipulating rigid objects, as we will see later. So what is our expertise, the expertise in our group? We work at the frontier between robotics and artificial intelligence. And as I said, one of our specialties is cloth manipulation. And we have this ERC project called CLOTHILDE for Cloth Manipulation Learning from Demonstration. And our approach to manipulating clothing, in this case dressing, you will see that is exploiting the collaboration between robots and humans. So there is like a transition, a way to automate.
It's my turn for breakfast this morning, Gromit. I like a 3-minute egg. Well, steady on. Oh, Gromit! Oh.
So you see, this would be the industrial robotics way or the industrial automation way of dressing people, which is not very comfortable for people, I must say. So we believe more in this human-robot collaboration in which each does what does better. In this case, the role of the robot is played by the dog, and this person is disabled, as you see, doesn't have arms. And what is interesting is that in the interplay, the interaction between the person and the dog, of course, the person has trained this dog before to do the right thing at the right moment, but you see that each of them has very limited capabilities. The dog can just use the mouth, and the person uses the body. But you see that using the characteristics of both complete the task, and the reinforce for its good behavior. So this was an example of this move I was saying from industrial robotics to assistive robotics. And this poses a series of research challenges. For instance, industrial robots were or are still programmed by expert programmers, while in assistive settings, there are not such expert programmers. Usually, the robots have to be instructed by non-experts. Then, in industrial settings, the robots are caged, meaning that they are surrounded by sensors. And if at some moment someone enters this cage, everything stops because it's very dangerous. Of course, if robots are to help dress people, for instance, they must be intrinsically safe. It's not possible to stop them because they wouldn't do the task. Another important thing is that in industrial settings, usually objects are rigid workpieces in production lines and so on. And in assistive environments, there are plenty of deformable objects, and in particular, clothing. What is the difference? The difference is that rigid objects, once you have the pose, namely the 3 degrees of freedom of position, for instance, like this, and 3 for orientation, the pose of the object is rigid, is fixed. You don't need to specify more things. While for deformable objects, imagine clothing, it can take infinite dimensional ways, no? Shapes. So manipulating clothing is much more difficult and need to be solved. Industrial robots aim at precision and accuracy, while this is a good thing or a favorable thing of domestic environments in which precision is not a requirement. Clothes can be folded not very precisely and nothing happens. So, but robots need to be tolerant to noisy perceptions and inaccurate actions. They should no longer behave through fixed sequences of instructions, always the same, repetitive, but should be capable of goal-directed execution. And of course, what I mentioned before, they should collaborate a lot with people and attain and perform tasks by the interplay of robots and humans. So I will show that some of these characteristics for assistive robots can be translated in features that AI needs to address. The easy instruction by non-expert and intrinsically safe for people can be termed as usability, easy of use by non-experts. That robots are able to perceive and manipulate non-rigid objects and be tolerant to noisy perceptions and inaccurate actions calls for intelligent ways of dealing with uncertainty. And being capable of goal-directed execution and collaborating with people calls for understanding. So it's not enough to give the right answer, but also the programs and the robots should have some understanding of what's going on in order to, for different environments, different conditions, attain the same result, the goal they are programmed for. So this has been termed the 3 U turns of robotic research in AI. I will now exemplify each of these 3 characteristics through some examples. So for usability, before the way to proceed was to exhaustively programming, taking into account all possible situations and having robots caged, as I mentioned. So what is the trend nowadays is learning from demonstration and control based on modeling robot dynamics for safety. So, for instance, as regards to learning from demonstration, in our lab, we program robots by imitation, learning by teleoperation sometimes, because this girl wears these motion capture sensors in the wrist and the arms, and you see that the robot imitates what she is doing. So it's a way for non-experts to easily program robots. Other times we program them by kinesthetic teaching, moving the arm of the robot itself directly. So as for safety, and in another prototype we have developed, that is to place a scarf here on a mannequin. So let's say in an assistive environment, the healthcare, this person, demonstrates how to put a scarf. And then at the execution time, the person, the user, can disturb the trajectory of the robot, as you see, stop it and so on, which could not do with an industrial robot. And you see that the robot behaves compliantly, but continues doing the task. And you see that this person, who is the one doing the research, really survived. And by the way, you will meet him today. I think he's the last speaker in today's schedule. And you see, since this person is the rector of UPC, and since he saw that some of the personnel was really placing his neck in this research, he said, oh, well, I will do it also. So he came to our lab, and we placed again the robot, the scarf on him. And we advised him that he could disturb the robot, but he didn't, so someone did, in order to demonstrate that it was safe. And well, I must say that afterwards, this got viral in the network, and some students just made a mock-up of this video in which somehow they threatened the rector that if they did not pass their exams, something not so nice would happen to him. Well, this is just a joke. Well, as regards to the other U, uncertainty, that robots in assistive environment should be tolerant to noisy perceptions and inaccurate actions. In industrial robotics, or in past applications, high resolution perception plus accurate manipulation planning were used. And the trend now is towards task-oriented perception, not perceiving in all detail all the scene, but just what is needed for the task, and probabilistic planning. So taking into account that some things could happen. It was not so accurately placed, every object, and therefore the robot should be adapted to context and to the user by learning through interaction. So this is an application we developed for a previous project called iDress that consisted in putting shoes to people. You know that grown-ups or people, elderly people, maybe have difficulties in placing shoes and socks and so on. So one type of robot of this kind could be useful for this task. And it will be shown that it is very important, and this I began to enter ethics issues, that the person feels that he or she is always in control of the situation. It's not treated like a workpiece in a production line. It's not cosified, as we say, but it's he or she is in control. So at all times, the robot informs of what it is going to do. So I will take the shoe from your hand, for instance. Actually, the robot speaks, and now it says, "Thank you for the shoe. I will now place on your feet. Please put the foot up." And I will approach now the foot. And if at any moment the person feels afraid and withdraw the leg, the robot would say, "Oh, I see that you are afraid. Would you like that I proceed more slowly? Or would you like that I approach you from a different direction, etc." This is to preserve at all times the dignity of the person and the control, that the person is in control. And for the third U-turn, understanding, most applications nowadays are that perform learning, perform associative learning, namely that given a perception, execute a given motion. But there is no understanding of what's going on, what the situation is, what the goal means. So there is no semantics. So a current trend in robotic AI is to attach semantics to perceptions, both of objects and of situations, and also reason about functionalities and goals. And this is important to adapt to different situations and also to provide explanations. You might have heard that one of the main research topics today in AI is explainability, being transparent for deep learning, for instance, being able to explain the outcome of an algorithm. So this goes in this direction. This application we have performed in our lab to help disabled people to eat, to feed people. You see, we have this arm that has a camera, a depth and color camera on the wrist of the robot. And when the person opens the mouth, feeds the person. The desideratum is that the robot would understand the situation, and in the case, for instance, that the person opens the mouth but is not looking at the robot, the robot should not feed until the person really faces the robot and wants to be fed. So, as I said, this is a desideratum. It's not that now we have implemented already all this understanding of the situation, but this is our goal, what we will like, that in front of unforeseen situations like this one, that the person closes the mouth just at the very moment in which the robot is going to feed him, then the robot that also has a force sensor in the wrist would stop and wait until the person opened the mouth. And here, well, this is an Italian student, and he, well, was very funny by closing the mouth in the moment that the spoon was inside. So this should be an unforeseen situation, or could be, and the robot should know how to proceed. So this is what we mean by understanding the situation that would allow us to deal with very many different possibilities and unexpected situations. So, having said this, let's focus on this CLOTHILDE project. We have envisaged 3 application domains for this versatile manipulation of clothing. One is housekeeping and hospital logistics, because as I said, there are many types of clothing items in such environments. Another application is in the automation of the clothing and internet business. You see, once people buy some types of clothes, usually they buy several sizes, for instance, or several colors, or several different items in order to see which one fit them better. And afterwards, they return the items they don't want to buy. And well, they come, like you see here, in a box, in any configuration, in any shape, and they have to be returned to the distribution chain, either by hanging them or by folding and putting them on bags, for instance. And this is all done manually. So if our project is successful, we will be able to automate part of this process. And the third application, which is the one actually I like best, is helping disabled people to dress, both for elderly people or people that has suffered an accident, or even in infectious environments in hospitals. It's important that the infected clothes are not touched by people. So this could be very helpful in situations, very useful in situations like the one we have been living in the COVID crisis, that some cleaning and some logistics of clothing could have been done by robots, but this is not yet ready. But even making beds and this type of things could in the future be done by robot manipulation. So, what theoretical tools are we using to tackle this theory of cloth manipulation based on computational topology? We are basically using, for those that are knowledgeable of topology and mathematics in general, we are using 2 constructs. One are cell complexes. What are cell complexes? This you see here is a small robot, is a planar robot that can only attain, has 3 degrees of freedom of positioning. The configuration space has dimension 3, 2 for position in the plane and 1 for orientation. So there are some configurations that lead to singularities. Singularities pose many problems for control. And singularities arise when actuators get aligned, when some degrees of freedom become redundant. So this is a representation of the configuration space of this small robot, and you see that these are the singularities and there are cells. So it's very handy in order to plan motions, for instance, to have a high-level representation of this decomposition of configuration space into cells, as you see here. So this is a tool we will be using. And another is persistent homology. Persistent homology deals with global characteristics of clothing, because not of clothing and many other things, many other objects. The interesting thing is that it is global, in the sense that geometry is details, like for instance in clothing, when you have wrinkles or small movements in the cloth, do not matter. So what is important is the general configuration, whether it is folded in one way, where it is it has holes, etc. And to just give a very, very simple example of how we are addressing this theory of cloth manipulation, how are we going to represent the configuration space of, say, a towel, a rectangular piece of cloth? As I mentioned, this would have an infinite dimensional state space. The number of shapes that the towel can adopt is infinite dimensional, as I said. So it's unbearable. We cannot manage this in a computer. So we have to simplify this configuration space. And as a first approximation, we just consider the corners. And we characterize the state of this by the determinants of 3 points in the plane. And here are all positive if we take the counter clock direction. For instance, the determinant of A1, A2, A3 is this plus sign, A1, A2, A4, also, etc. All follow this direction. Now, if we have another configuration in which this vertex has come here, then there is one determinant change sign, the A1, A3, A4, this one. And moreover, if this corner traverses this other line, then we have two determinants that become negative. The A1, A2, A3 also becomes negative. So we can very globally represent these 3 states by these determinants of 4 points. And this very simple representation leads to this graph that is a simplified representation of the configuration space, in which these rectangles are the different states of this towel, say, and the ellipses are the singularities, that the links that permit passing from one configuration to another, so that we can plan motions for going from this state to this state, as was exemplified in the previous slide. Then we have to move in this direction and then this direction. So it permits representing this difficult configuration space through a graph and transitions in this graph. Of course, it gets a lot more complicated because you need to represent many more points, etc. So this is one of the works we are doing in this representation of configuration space. Another is linking this to vision. In what sense? We train, in this case, using deep learning, as you saw yesterday, from several data set of RGB images, static images of this cloth in different positions and orientations, different shapes. We train a deep learning network, and we associate the labeling, the outputs are the 3D ground truth, because since it's through simulation, we have the ground truth. And the idea is that when we are presented with, for instance, this image, that the network outputs exactly the 3D mesh in space, that then can be linked to the labels provided by our representation of configuration space that I mentioned. But this is not enough, because this was all static. We had images and positions and poses of cloth that all was static. Moving from one configuration of the other was just moving from one static configuration to another. But a lot of what is done with clothing is dynamic, and it has a complicated dynamics. So we devised a model based on the mechanics of inextensible surfaces, because you see clothing is very deformable in one, getting it out of the plane, but it's not so extensible. So this is hardly modeled with usual procedures in computer graphics. So we had to extend this and include friction and collisions. And then we tried to learn how to learn dynamic manipulation of clothing. For instance, this is static folding. This is what will be grasped by the manipulator, and this is the goal. So in this case, it's almost as a rigid motion, going from here, slowly getting here. This can be learned with usual deep reinforcement learning procedures. But when you only pick up this vertex, this corner, and you like that both this one and this one get folded here, so it's turned, and you are controlling a distant corner by just grasping the cloth by this corner. Sorry, I didn't mean to pass the slide. And this is another type of dynamic manipulation of clothing, which is holding the cloth by these two corners, reach that these two bottom corners reach this goal position. So here, with two grasp points, we have to control two distant corners. And this is learned through reinforcement learning. If you like, I put here below the references in case people like to look at it. So you see that by using this procedure, that, well, it's trained with randomization, with the reinforcement learning using hand-side experiential rewards, and also demos. I mean that the user can demonstrate, but after a while, the right policy is learned. And just to mention that this type of learning is much more difficult than learning pick and place of rigid object, for instance. Well, it can be seen, because here there are many more variables that matter, like, for instance, speed, the trajectory, etc., leads to different final configurations. Well, another important issue that we are dealing with, you see that this project CLOTHILDE is like a puzzle. There are many pieces, and at the end, they all should fit together in order to attain this versatile manipulation of clothing. And another is, of course, identifying where to pick up, where to grasp clothes. You will have an entire talk today by Julia Porras on this grasping thing, but just to advance a little bit what will be shown, grasping of tissues, of clothing, is somehow dual of soft grippers. You might have heard of soft grippers that adapt to objects, and they help grasping rigid objects without having very much precision, without having closure grasp. And somehow dealing with clothing is the opposite, because it is the object, the cloth, that adapts to the shape of the gripper. She will elaborate on this. So we have devised a taxonomy of possible grasps needed for grasping and have identified what grippers are there being used for grasping clothing and what is missing also. So, and the last point is learning robot skills from demonstration and reinforcement learning, because, and this will be a presentation also by Adrien Colomé later on today. But just to give you a glimpse of what it entails, as I was saying, it is, the robots should be easy to be programmed by non-experts, by, for instance, healthcarers or people that do not have expertise in programming. So for dealing with clothing, one thing is using reinforcement learning, but it's not enough, because you see that people sometimes has difficulties folding clothes like this one. Well, this one is the one doing research on this. It's Adrien Colomé, and he does it very well. But look, when he has to entrain these two arms to do the same, it doesn't lead to a very nice result. So somehow it's necessary that the robot rehearses itself, exercises, and through a cost function that measures how well the cloth fits a rectangle, and if it's wrinkled or it is not, then it begins to make slight modifications of the initial movement in order to keep improving. This, as I said, will be extensively explained by Adrien in the last talk of today. And you have here some references if you like to look at them. So now, you see, working in this assistive context raises many ethics and social questions. So we have become very involved in dealing with these questions, as you will see. And there are some issues that are shared with previous technologies since the Industrial Revolution. For instance, the incidents on the job market, the legal liability, privacy, digital gaps, all these are not new. Computer science and other machines already introduced all these issues. But what is new about these robots interacting in everyday life with people and artificial intelligence taking decisions for us? Well, that these new issues have to be dealt with. And, well, you have seen that there is quite a lot of concern in the media and in the citizenship in general about them. Why? Because, as I said, these type of technologies can take decisions for us, not just suggest decisions, which is very nice, but also sometimes take them automatically. There are communication issues because these technologies act as vehicles of our communications. They interfere in our feelings and relationships. People even get attached to the Roomba robot to say something, and when they go on vacation, they say, "Oh, I will take my Roomba robot to vacation because how can I leave it alone?" Things like that. You might think that this is science fiction, but it's not. I mean, people say these things. And also there is all the topic of human environment. When there will be implants that there are already, some will have access to these very sophisticated technologies and many people won't. So there will be digital gaps that are different from previous ones. So as I was saying, people establish ties with machines, with robots. Some of these ties are physical. So exoskeletons, artificial arms and hands, sensorized dresses, telepresence, artificial retinas, implants. All these are robotic prostheses that extend the body and potentially give more autonomy to people with disabilities. So they are perceived as beneficial inventions or innovations. But there are other ties that humans establish with robots and machines that are, I would label them relational. Living with artificial nannies, learning from robotic teachers, sharing work, leisure, and affection with humanoids will enhance the intellect and social habits of people, will help develop new capabilities. These are the questions that are dealt with in an ethics setting. And as I mentioned, the robotics community and the artificial intelligence ones are getting very concerned about all these implications. And some years ago, not many, this new discipline, Roboethics, was established, which is a subfield of applied ethics, studying both the positive and the negative implications of robotics and AI for individuals and society. I always like to make this distinction that what is good for an individual may be bad for society and vice versa. So all these ethical considerations have to be taken into account both, and depending on the context, should be made concrete in one direction or the other, as we will see. And there are two branches of robot ethics. One is human ethics applied to robotics and AI, so the ethics that has been developed by philosophers since many years ago. And this is, in my opinion, the most important part, because ethics is a human endeavor. But there is another part, another branch of ethics, which are codes of ethics embedded in the robots and the programs themselves, what has been termed machine ethics. There are many people working nowadays on putting values directly within programs so that they can not cross certain red lines, say. So this is an important research domain nowadays. So, moreover, robot ethics is approached from two different stands. One is developing regulations and standards, and the other is education and getting or forming public opinion. As regards to regulations and standards, there have been many initiatives. For instance, in 2017, the European Parliament approved some civil law rules on robotics, which were extremely general. There were very 6 principles derived from human rights, essentially. That the intention was to set up a core that other organizations, other countries could specialize, could particularize to particular cultures and circumstances. Because you see, each culture has some values, and you cannot make really very concrete guidelines for every country, for every situation. And the high-level group on AI in December 2018 also published these ethics guidelines for trustworthy AI. And well, there are also projects like this AI for Europe that are developing these guidelines that are open to the community, in the sense that they are all in internet, and they are intended, as I say, for different professional organizations, different governments, etc., to take them and make them concrete for their particular contexts and uses. And the IEEE, their Standards Association, like 4 years ago, opened this ethically aligned design draft to public discussion. And finally, last year, it was published as a document with 500 pages, touching on 18 big issues, like robots in the workplace, robots in education, in the healthcare, etc., and has a committee for each, and they got all the feedback from people, because they are, again, this document is open in internet, anyone can download it, and before it was possible to make comments. So it has been adapted to many different cultures and situations, and I really recommend that you have a look at it. Well, but I'm very much in favor of regulation and all this and standards, but I'm more in favor of education and dissemination, because I think it's crucial. And in this sense, I like that the ACM, IEEE associations published this curriculum on computer science that has 18 knowledge areas, and one of them is professional practice, social issues and professional practice. That includes courses on ethics in technology, robot ethics, professional ethics, etc. And Barbara Gross, who is a professor in Harvard, she says that by making ethical reasoning a central element in the curriculum, students can learn to think not only about what technology they could create, but also whether they should create that technology. And these courses are taught in the United States, in Canada, etc., using philosophical textbooks and papers. But these sometimes for technology students are a bit too abstract. So nowadays they are more in favor of using science fiction readings, essentially from Asimov, Bradbury, Philip K. Dick, etc., meaning classical science fiction. You see why? Because, for instance, Neil Stephenson, who is a very renowned science fiction writer, he says that science fiction stories can do better than almost anything else to provide not just an idea for some specific technical innovation, but also to supply coherent picture of that innovation being integrated into a society, into an economy, and into people's lives. So this is the use of science fiction in teaching ethics, anticipating possible future scenarios. And Judy Goldsmith, she's a university professor at Kentucky, and she's been teaching ethics based on science fiction for 7 years already. And she says that using fiction to teach ethics allows students to safely discuss and reason about difficult and emotionally charged issues without making the discussion personal. So it helps engage technology students much better, I would say, than very elaborate academic ethics texts. Very quickly, because I'm running out of time, there are many initiatives in the network to teach with science fiction, not just robot ethics, but in particular also robot ethics, like this Teach with Movies based on the movie Robot and Frank. There are others based on this movie Ex Machina. There are series. I recommend very much Black Mirror. It's, in my opinion, a masterpiece that takes all these technologies in each chapter, one of these technologies, and dives it to the last, the extreme consequences. Real Humans is a Swedish series that places robots everywhere in human lives. MIT Press is very interested in providing materials for these courses and has started publishing fiction by scientists, in this case by Ilya Nurbash, who is Carnegie Mellon computer science professor, and that teaches a course based on some short stories that he wrote in this book, Robot Futures. And I also wrote a novel in English called The Vestigial Heart that has as leitmotif what you see here. It is the relationships that we have constructed, which in turn shape us. This was a saying by Robert Solomon, who is a philosopher, and that said this in relation to our parents, our friends, our teachers that shape the way we are. In the same way, if we are interacting a lot with technology, this technology is already shaping us. So we should better think twice what technology we are developing, because this is the technology that is going to shape us and our future generations. So, well, just very quickly, this novel is published together with an appendix with 24 ethics questions. And then there is some online teacher guide and 100-slide presentations in MIT Press website for professors and teachers to download and adapt as desired. And of course, students can download it as well if they ask for permission. It deals with all these topics: designing the perfect assistant, robot appearance and emotion, robots in the workplace, robot in education, human-robot interaction and human dignity, social responsibility and robot morality. And there is also some bibliography and other initiatives to follow up. I am running out of time, so just very, very, very quickly, what is the structure of these chapters in the appendix? For robot appearance and emotion, and the others as well, there are some highlights from the novel, because all these questions are set in a specific scene in the novel. Then there are some questions, 4 questions in each chapter, and hints for a debate, and then revisiting issues and some scholarly references, as I said. I won't go to the headlines. Just very quickly, for instance, the questions on robot appearance and emotion. How does robot appearance influence public acceptance is one of the questions. What are the advantages and dangers of robots simulating emotions? Have you heard or experienced the uncanny valley effect? This effect you might have heard is that people get attached to robots the more they resemble human beings. So the more they resemble, the more they get attached, up to a point in which if they are too similar, like this female robot, but there is something strange in the look, then the attachment drops abruptly. This is the uncanny valley, because it's very, well, it creates like a bad sensation of repulsion. And well, this provides some hints on how robots should be designed. And another question is, should emotional attachment to robots be encouraged? Well, I think I will stop here. And with these future amazing perspectives, in my opinion, because I'm very fan of technology, as you can imagine. I am developing these robots. So I'm very curious about what role will the human and the robot play in this passade in which we are irremisibly engaged, because robots are here to stay. So we have to really devise them in good ways for both individuals and humanity in general. And as I said at the beginning, we are hiring for this CLOTHILDE project, especially people that has background on topology, computer graphics, and machine learning. So please look at our web, CLOTHILDE web, and send us a mail. Mainly in our web, there is a part that is called Join Us. Please look at it and send a message. Thank you very much.